Okay, let's begin today's seminar. Arendelle-ftl. They will begin a new seminar about cosmology. Okay, so first things I will talk about something about the reference book. There are several textbooks on cosmology, and well, I will refer to some of them. The first one is Physical Foundation of Cosmology by Mukhanov. Mukhanov. I think he's a Russian professor. No. Okay, he's in LMU now. Well, this book is focused on the very early universe, and because the author is one of the founders of inflation theory, so this book is particularly good in the introduction of inflation. Okay, the second one is the classical textbook, Modern Cosmology. By Dodelson. Well, he's a former professor in Chicago University, but now he moved to somewhere else, I suppose. And third one is the newest cosmology textbook, published in about 2022 by Daniel Baumann, a professor at University van Amsterdam. It's a new book, some inspiring feature in it. Okay, so much for this. I will refer to some book sales, maybe in some tricks or details, but mainly these three ones. Okay. So about the content of this seminar, of course, the cosmology the cosmology seminar always divided to two parts. The first one is the topics about homogeneous universe. Well, there's some basics topics about this. The first is the foundation equations, which we will talk about this today. Fundamental equations. Particularly is the Friedmann equations and Boltzmann equations. The first one will govern the expansion history of universe. The second one will describe the thermal history of this expanded universe. And using these two fundamental equations, we'll construct the hot Big Bang model. And something about the early universe. And last topic about the homogeneous universe is inflation. Inflation. Okay, and the second part in homogeneous universe. Well, we'll include mainly two topics. The first is the perturbation theory, including the growth structure and the perturbation theory for inflation, and CMB, the cosmic microwave background. Okay, so much for this. This is the main content of this seminar. Okay, today we will only talk about the fundamental equations. We'll derive Friedmann equations and Boltzmann equations. So let's begin. Well, I think I should Okay, fine. Fundamental equations. First one is Friedmann equations, which I just said about. We are governing the expansion history of this universe. So, another thing, we will before we begin to derive these fundamental equations, notice one thing that about the knowledge of general relativity. I will assume that you have the basic knowledge of GR, including the definition and properties of such as metric, Christopher symbol, covariant derivative, Ricci tensor, Riemann curvature tensor, and so on. Because this is a cosmology seminar and I have no time to derive all these basics things in GR. Maybe in October I will hold another separate seminar mainly focus on GR. Maybe if I have time, I may start with the definition of topological space. But now this is a cosmology seminar, so I will assume you have this very basic knowledge about general relativity. And another thing about the unit we will use a natural unit, which means h bar equals to z equals k, Boltzmann constant equals 1, and a metric minus positive, positive, positive. Okay, so much for this. Let's begin. First, we will talk about Hubble law. Actually, it's an observation law. It's describing the expansion of the universe. So first, we will show two facts obtained from the observation fact. The first one is the universe is homogeneous and isotropic on a large scale. This large scale is very important because if you turn to a smaller scale, you will find the universe is absolutely not homogeneous as isotropic. And for example, there will exist the galaxies and the suns and such as the Earth. But if we turn to a sufficient large scale, we will find the universe is homogeneous and isotropic. Homogeneous means that actually we can explain homogeneous and isotropic as two symmetry property. The homogeneous means you can make a translation and the object will not change, and the isotropic means you make rotation and the object will not change. Or you can say that homogeneous means every point in this universe is equivalent, and isotropic means that every direction is equivalent, such as that. Or just a different explanation. And the second one is this universe is expanding. Actually, we can base this. We can obtain the Hubble law based on these two observation facts. Yes, and so we can use these two basic facts to obtain the expansion law. First, let's assume that there's A and B. A, B equals R. Well, suppose the observer is located on B, and the velocity with respect, expansion velocity with respect to A will be A equals to, we don't know the expansion law that suggests it's a function about R, A, and T. Well, actually, because the universe is homogeneous and isotropic, so we can restrict this function on some properties. For example, because every point in this universe and every point and direction is equivalent, so this expansion law will be valid between A and B and C, and C and A. So and because the homogeneous and isotropic properties, we know that this expansion velocity v shall parallel with this RBA. So and about this, we can use this equivalency to construct an important property of this expansion law, V3. If V3 equals to V2 minus V1, well, then FR3 equals FR2 T minus FR1 T. So let's use this diagram to represent it. If RAB equals R1, and this is V1, RAC equals R2, this is V2, and RBC equals R3, this one equals V3. Obviously, R3 equals R2 minus R1. So we obtain FR2 minus R1 T equals FR2 T minus FR1 T. So we can find out that this F is actually a linear transform with respect to R in the Euclidean space. Transform with respect to R. Okay, and we know that F is parallel to R. And we can easily prove that it's an endomorphism, because such as you can use just make the R1 equals R2, and you will obtain that F0 to 0. And above all this, you can always find a basis that in which this linear transform can be represented by a diagonal matrix. And this diagonal matrix can be represented as a constant times the unit matrix. So above all, we obtain this one. V equals HT R. And this constant, which is relevant, which contained in the time variation, because this expansion law, this homogeneous and isotropic property is on the space, so we can leave this t variable here, and this expansion law contains this constant, which has a famous name, this Hubble parameter. It's a famous Hubble law. Okay. Okay. Let's rewrite this. We cos. Okay, so now we should figure out that how can we represent this HT in another way. In the three-dimensional expansion space, maybe it will be difficult to think about it, but we can make an analogy. Well, to a two-dimensional surface of an expanding field. Make a picture. So just like this. Let's consider the two-dimensional surface field. And this is A, this is B. This radius A will increase in when the time increase, and this is the theta dimension R. So according to the geometry knowledge, we know that R equals AT theta. And make a derivative with respect to t, we will obtain that v equals r dot equals a dot t theta. And we can make a substitution of this a dot t with theta, and we obtain a dot t over a t r. So in this analogy, we obtain that the corresponding ht will be a dot t over at. Well, in this analogy, this A has a geometry meaning. It's just the radius of this sphere, but in the three-dimensional expanding universe, we cannot make such. We cannot make. We cannot get a clear geometry meaning of this parameter, but we can make a similar formula, because the three-dimensional expanding universe is just an analogy to the two-dimensional surface of a sphere, and we can write as RBA HT. This is the velocity. And we just integrate this formula with regard to t, dt. Yeah, and now we will obtain RBAT called AT pi. Well, this AT is the analogy with the above radius, but but in the three-dimensional expanding space, it can be chosen arbitrarily, and this chi BA is called the co-moving coordinate of the point B with respect to A if we centered a coordination at point A. Okay, so this HT Hubble parameter will cause A dot over A. And this one is the parameter measuring the expansion rate. Notice that we only consider the this A dot over A. So if you make an A to a scale factor lambda A, the HT will not change. So this is just a renormalization factor. Okay. It can be chosen arbitrarily. Okay, so much for this. Now we have turned the Hubble law, which is the expansion law of the expanding homogeneous and isotropic universe. Now we can try to discuss the dynamics. Well, first we will use Newtonian theory to obtain some intuition. Then later we will use general relativity. But first, we should try Newtonian method. No, it's Newton. Well, this dust is all we can use dust or matter, which both of which has meaning that it represents the non-relativistic particles. So for dust or matter, we mean that it's non-relativities. So the pressure is much less than the energy density, and velocity is much less than c. In natural units is 1. Okay. So let's consider a sphere where the radius is r, and we can use the above formula to rewrite it as RT equals AT chi. This chi just represent at some time t0 the magnitude of this RT over AT. Okay. So we can calculate the energy density epsilon equals 4/3 pi r cubic. And this one can be written as this formula. T cubic. Well, this epsilon just the energy density at the moment at which the radius is equals to A0. And we can make an derivative with respect to t on the both sides of this equation. What's wrong with it? Okay. Just make a ddt over this both sides. And we can then epsilon t dot equals -3 0 A0 over AT cubic A dot over A. Notice that this is just the definition of Hubble parameter, so it equals -3h epsilon t. We obtain this equation. We should notice that this is actually the continuous equation for in a non-relativistic condition. To see that, we can rewrite it just as partial epsilon partial t equals minus the divergence of epsilon v. This is the continuous equation of in non-relativity forms. To see that these two equations are equivalent, just use the Hubble law. V equals HTR. And notice that divergence of R is equals to 3. We have this formula. The most simple way is to derive this, just use the spherical coordinate polar form of divergence. For example, there is A with 3 components, theta, A phi, in a spherical polar coordinate. So this one equals to r square over 1 partial r square AR as r sine theta partial theta sine theta A theta as r sine theta times partial A phi partial phi. Okay, for this vector r is just r0, 0. So substitute in this expression of divergence in spherical polar coordination, we will find that this result. Okay, so much for this. Let me see. Okay, now let's assume the matter outside this sphere we have considered does not exert the gravitational force on the particle inside. Actually, this assumption cannot be proved. Just use Newtonian theory. But now we just admit that and to see what will happen. Now we can derive the dynamics of the dust inside this field. Use Newtonian gravity law. G over R square. Recall the about the equations above about the energy density pi r cubed. It equals to epsilon 0 a0 at cubic and RT equals AT. Okay, combine this equation, we will obtain that the second derivative of A equals minus 4 pi over 3 G epsilon A and equals 4 pi 30 G epsilon A0 square. Okay, and multiply the one-order derivative of A in both sides of this equation and make an integrate. We will obtain 1/2 the square of A dot. Well, I will write it down explicitly. Well, this A double dot can be written as the A dot over dt. Okay, we multiply A dot on both sides and integrate with respect to dt. Equals to the right side is I3 G epsilon 0 A dot over A square dt. And the left side equals 1/2 A dot square. This equals to positive 4 pi over 3A G epsilon 0 A0 over A. And consider the integral constant, we obtain this equation 1/2 A dot square minus 4 pi over 3A G epsilon 0 A0 cubic over A equals the integral constant, and we can name it the energy E. And use the definition of Hubble parameter, we can rewrite this as h squared minus 2e over a square, of course, 8 pi g over 3 epsilon. Okay. This is just the dynamic equation in the Newtonian gravity theory cosmology. Okay, later we will find out the real Friedmann equation using the general relativity, and we will see that these two the general relativity forms can be reduced to the Newtonian one in some conditions. Okay. Okay, so much for this. Now let's begin the relativity cosmology. Okay, first, we have known in general relativity that if we obtain the metric, we can calculate the affine connection or just the component of Christopher symbol, and then we can use them to calculate the Ricci tensor and Ricci scalar and the Riemann curvature tensor, and finally using the Einstein's field equation to obtain the dynamic equation governing this physical phenomena. So first things we should do is that we should obtain the metric of this homogeneous and isotropic expanding universe. So we will first obtain this metric, and this metric has a name, Friedmann-Robertson-Walker metric. Or we can just call it FRW metric. So how to obtain this metric is it's a little tricky things. Okay, so notice that the space is homogeneous and isotropic as I have said in the beginning of the seminar. So homogeneous is actually is a symmetry property, which means that if you make a translation to the object and it will unchanged, it won't change. And isotropic means that if you make a rotation to this object, it will unchanged. So actually, let me think how to. You can just use this operation to define this symmetry, and you can find that the most simple space obeying this symmetry is just a flat space. Where the line elemental DL square. Notice that this DL is just a three-dimensional. Is it just in three-dimensional space, not relevant to time? We are talking about. We are only talking about space up to now. Yes, it's 3D. Okay, I will ignore the 3D afterwards. So this dx square will not change if you make a translation or rotation to this in this flat space. So obviously it updates this symmetry property. And the second one is spherical surface is a spherical surface in a four-dimensional Euclidean space with a radius a. And we can represent the line element as dl square equals dx square as dz square, and z square as x square, a square. Yeah, this is just a parameter. To understand this situation more intuitively, we can just make another analogy in a lower dimension. Now we just consider a two-dimensional spherical surface in three-dimensional Euclidean space, and we can see it. X. Oh. Just like something like this. Okay, the radius is A. And we just consider the geometry of in this surface, including this DL. We can find that if we fix the XZ and just rotation around the XZ, we will find that this DL, this length with this little length won't change. And actually, in the two-dimensional spherical surface, this rotation means that change of the direction of vector. And there's another rotation in this three-dimensional Euclidean space that will change z and can represent the translation in this two-dimensional spherical surface. and both operation won't change DL. So actually, this situation is a case that obeying that obey the homogeneous and isotropic property. Okay, this is just an intuitive description, an intuitive and descriptive way to understand this. And if you want to uh, solve these questions more rigorously, you can use the group theory. But now we will not talk about that things today. Okay, it can be proved rigorously, but not today to discuss this. Okay, this is the second situation, and the third one is consider hyperbolic surface in four-dimensional pseudo-Euclidean space. Hyperbolic space, and this and the space line element cos dx minus dz square and z square minus dx square over a square. Well, this one has not a lower analogy, which we can see very clearly because it's not a Euclidean space; it's a pseudo-Euclidean space, and you see that the matrix including minus sign in here. So you can the rotation in this case is just like the Lorentz transforms. Although in Lorentz transform, this parameter z is just time t, but here is just a space parameter. Okay, I will not draw a picture to represent this. So to summarize all the three situations, we can just write the L square as this, supposed to well, wait a minute. Okay, fine. So to summarize all the three conditions above, we can use we use one expression to express them all, and just make a transform. Make a scalar transform. You make x to ax, z to az, and we can write down the dl in one way, in one expression, dx square z square square. Okay, and to simplify this one, we don't want this parameter z to be shown up in this expression. So we try to eliminate it, make a differentiation of this expression. We obtain z dz as or minus x dx equals 0, and use this expression to eliminate z. We'll find that the L square cos a square dx square positive as or minus x dot dx square over 1 minus x square. And so we can just introduce a parameter k to express it in a more beautiful way. X square at k x dx over 1 minus kx square. Well, in these equations, k can run to positive 1, minus 1, and 0. The positive one means spherical. The spherical case we have just talked about, just like a spherical surface. Although this surface is actually a hypersurface and the dimension is 3. And the -1 means the hyperbolic one, and 0 means flat space. Okay. So to obtain the line element in this three-dimensional space, and we can write down the time space distance dl square in this four-dimensional space-time equals minus dt square dl square. Yes, and equals is equals minus dt square as a square. Notice that this a can depend on t because it can generally depend on t. Square x dot dx square over 1 minus kx square. Okay. Notice that dx can just be written as g mu nu dx mu dx mu. Yes, and in this case, we can just write down the Gij. Notice that if I use the Greek number, it ranges from 0, 1, 2, 3. The Greek what's that? Greek character? No. Just like if we use the Greek ones, we mean that it can range from 0 to 3, and it can represent time t. But if I use Latin one, it just can range to 1, 2, 3. Okay, just a space component. A square delta ij as k xi xj over 1 minus kx square. Okay. I can explain this one in a general way that if we want to, you can just understand it in the matrix form. It's just like dx1 is to dx3. It multiplies this matrix. And we obtain this one. So we can just write down the component of this matrix x square, x1, x2, x2 square, x3 square. And it's not difficult at all. Okay. So this is a famous FRW metric, and of course we can write it in a more beautiful way in spherical polar coordinates. Fine. Copolar. Just this dx will, yes, this dx square will become dr square as r square, d theta square as r square sine theta square d phi square. Like we write just as dr square as r square d omega, and this omega is d theta as sine theta square d phi square. And the FRW metric can be written as dx square over O equals minus dt square at a square t dr square over 1 minus k r square as r square d omega. Okay. So I've obtained the FRW metric, and next step is to calculate the Christopher symbol, the Riemann curvature tensor, the Ricci curvature, the Ricci tensor, and the component of the we will use in Einstein field equation. And now let's begin to calculate. First, we will introduce the gamma ij. it actually just the three-dimensional special metric is equals Gij. It's three-dimensional special metric. Okay. We'll use this gamma ij later. Okay. So recall the expression of Christopher symbol with respect to metric gamma lambda mu u cos g lambda rho g rho mu as g rho mu g rho mu minus g mu rho. This comma means just the partial derivatives over x over the coordinate. Yeah, it's the definition. Okay, so we can, because we have obtained the FRW metric, and we can just easily calculate the component of this Christopher symbol. Obviously, if gamma has more than 2 time indices, it will vanish. It can be verified easily. No. 2. Yes, it can be verified easily. Okay, and so we need only calculate the 3 different case. The first one is gamma 0 ij. If you just substitute the FRW metric into this expression, you will easily obtain it equals a times a dot times gamma ij. Yes, and gamma I 0j equals a dot over a delta ij, or it can be expressed as Hubble parameter delta ij. And third one, gamma ijk, the complete special component of this this Christopher symbol, gamma il. JLK as gamma KLJ minus gamma JKL. Well, notice that this expression is just the same as the general expression of gamma in the n-dimensional space. So it can be defined. So it just can be defined as the 3-dimensional metric Christopher symbol. We use this tool to distinguish it from the general Christopher symbol. Okay. And actually, strictly speaking, the next step we should try to calculate the general Ricci tensor. But actually, but if you calculate the straightly, it will be very annoying. And there's also a trick to just simplify this calculation. Notice that because we have a homogeneous and isotropic universe, so we can choose a world time such that this gamma ij, this space metric, is assigned at all points in all directions. It can be done because we have a very good symmetry property in this space. So we can, so you know that the curvature of the space is completely determined by the Riemann curvature tensor. So we introduce the three-dimensional Riemann curvature tensor are tuned IJKL. We use this tuned to distinguish it between the general Riemann curvature tensor. And we have known that the space has the two symmetry property. So, and the symmetry cannot, and we know that we can choose over time that the symmetry, that the metric won't change at all points and in all direction. So the Riemann curvature tensor can be written in this form. Can only be written as this. Because in this universe it can only depend on the metric, if the metric is the same at all points in all directions, the derivative will vanish. So we can just write down this three-dimensional Riemann curvature tensor with some coefficient IL gamma JK at C gamma IK gamma JL. Well, next we should determine these three coefficients, A, B, C. Now we shall use the general properties of the Riemann curvature tensor. Because it's a general property, so it of course the three-dimensional Riemann curvature tensor will obey this property. This tensor is anti-symmetry with regard to the first two indices and the second two equals 0. And another one, IJKL, if we just exchange these two set of indices in a total, it won't change. KL, IJ. Okay, use these three properties and notice that gamma IJ is a symmetry, is a symmetry metric. It's a symmetry matrix if you represent it as a basis. So we can just obtain that A equals 0 and B equals minus C. So we obtain that this three-dimensional Riemann curvature tensor R2 IJKL is just a constant times gamma IK, gamma JL minus gamma IL, gamma JK. Okay. And we know that according to the definition, the Ricci tensor in this three-dimensional space equals the contraction of indices of this Riemann curvature tensor. Just we can just write it down. Will be 3 gamma ij minus gamma ij. Okay, equals 2c times gamma ij. So we obtain a simple expression of this Ricci tensor in three-dimensional space with respect to the metric, the three-dimensional spatial metric with just a coefficient C. Now we know that because we know the space is homogeneous, so this relation can be held anywhere in this space, and so we can just choose one particular point and to derive the relation between the Rij and gamma ij and find out this C, and it will be valid in the whole space. It's just the logic. The logic is here. Now, how to down the most simple point in this space is of course the origin. So let's begin. Recall the expression of gamma ij. Gamma ij is just the space component of the metric Gij, and it equals a square delta ij minus k xi xj minus 1 minus k x squared. Now we want to treat the situation that at the origin, so we can just set the x equals to 0. Then gamma ij becomes a square delta ij at k xi xj. Now we can just use the formula for Christopher symbol to calculate this one. This space, this three-dimensional space Christopher symbol, gamma, at the origin point, of course, gamma JLK as gamma KLJ minus gamma JKL. Okay. Just substitute this expression of gamma and calculate gamma IL. Well, this is a partial xk, k times a square xi xj, and so on. And we know that this is just ka square times delta jk xi as delta ik xj. And the latter terms is the same. And above all, we obtain the calculate use the very simple calculator where we obtain that it equals 1.5 k a square gamma il times 2 delta jk xl, and it can just be written as a square k delta ik xi. This expression will be very important in the following derivation, in the following derive. Okay. So obtain this. Now we can just to calculate the Ricci curvature, the Ricci tangent in the three-dimensional space. It's recall the formula, recall the equation, the definition. Well, it's not definition, it's just calculate method of this, the component of this Ricci tangent, k ij k. Okay, as gamma tilde mik gamma k jm minus gamma tilde kij kij gamma tilde mkm. Okay, if you substitute the expression for gamma, you will find the latter two terms will just vanish. And the first two times, partial xj is square k delta ik xk minus partial xk a square delta ij xk. Notice that the first one, first term is just delta ik times delta kj. This one is just equals to delta ij. Because if you sum up this k, then it will obtain only when the k equals to j, the second term will not vanish and equal to 1, so it just equals delta ij. But the latter one is not correct. It's not the situation. It will be delta ij delta kk. This delta kk, if you use the Einstein summation convention, it will be just delta 1 as delta 2 as delta 3. So you will obtain a factor 3. And so it equals to 3 delta ij. And finally, it equals this Ricci tensor equals 2a square k delta ij. And notice that this gamma ij equals a square delta ij as something else as a higher order of xi. If we choose at exactly the x equals to 0 origin, there the metric is just a square times delta ij. So this expression can be rewritten as rij equals minus 2 k gamma ij, which we have known that in general, in the whole space, these are R2 ij equals 2 times the constant c times the gamma ij. And in the origin point, we know that the constant is just k, and the constant should not depend on the point because of the homogeneous and isotropic property of the universe. So we obtain that in general or in anywhere, R2 ij equals minus 2k gamma ij. Okay. So let's come back to the all above discussion is in the three-dimensional space. Now come back to the four-dimensional real space-time. We will calculate the four-dimensional Ricci tensor R mu nu. Notice that obviously R0I equals R, I0 equals 0. Because these three vectors and a three vector in this homogeneous universe will always vanish. Recall the Christopher symbol. We calculate from the FLW metric. A dot gamma ij gamma I0j equals a dot over a delta ij. Now we can calculate this one in general, and we will substitute in the Einstein field equation and obtain the dynamics equation. First, the time components are 0, 0, cos gamma I0 I0j gamma J0I. The only terms which will not vanish, and it equals partial t a dot a delta. Just use the expression delta II. Notice that it will give you a factor 3 because of the summation. As dot over a square delta ij delta ji. This is just equals to delta ii and equal to 3. Also a factor of 3. And finally, we obtain that it's just 3 times d dt a dot over a as a dot over a square cos 3 a double dot over a. Okay, and the complete space component Rij just expand the calculation equation. K J. Notice that all the Christopher symbol have two time components will vanish. So the only not vanished terms is just J. Sorry, gamma K Ijk as gamma 0 Ij 0 as gamma M Ik gamma K Jm as gamma 0 Ik gamma K J0 as gamma M I0, gamma 0, Jm, minus gamma k, Ij, gamma m, Km. Yes, as gamma 0, Ij, gamma m, 0m. Yeah. And just rewritten this above expression, obtain that it's just the space, the three-dimensional space which tender Rij2 minus gamma 0 Ij 0 as gamma 0 Ik gamma k J0 as gamma m I0 gamma 0 Jm minus gamma 0 Ij gamma m 0m. Okay, so let's explore the value of each terms. This one we have obtained gamma ij, no. This one is just the gamma ij d dt a times a dot. And this one, write down the expression of the Christopher symbol, gamma k, a dot over a, delta kj. So it equals a dot square, gamma ij. And this one just, it's actually just the interchange I and j, so they equals to here. It always equals to this term and this one, a dot gamma ij, a dot over a, delta mn. Notice that this summation will give you a factor 3. Square gamma ij. And we finally obtain the complete expression Rij equals R2 dij minus 2 square gamma ij plus a total gamma ij. So it equals minus 2 to k as 2a dot square as a times a double dot gamma ij. Okay, we have finally obtained the complete Ricci tensor in this expanding universe. Okay, and the final step is just substitute this Ricci tensor together with the metric and the energy momentum tensor to the Einstein equation, the Einstein field equation, and obtain the dynamic equations. So let's do this last step. Famous Friedmann equation. Recall the Einstein field equation. R mu nu equals minus a 8 times pi g. T mu nu is the energy momentum tensor minus 1/2 g mu nu, and the trace of this energy momentum tensor. And according to the definition, T mu nu equals epsilon p p p. This epsilon is just the energy density, and the p is just the pressure. At original point, of course, not the general expression. Now we can just easily calculate the time. Okay, we have obtained the Ricci tensor, these Ricci tensor Rij and R00, the time components and the space components. Just substitute it to this formula, to this field equation. R00 equals, use these time components we obtain 3a over a equals 4 pi g 3p at epsilon. And the space components we obtain 2k as 2a dot square as dot equals 4 g a square epsilon minus p. Okay, if we want to eliminate this the second order derivative of a, just use these two equation to eliminate this variable. We obtain that a dot square as k equals 8 pi g epsilon a square. And if you use the definition of the Hubble parameter, we obtain the h square as k over a square just equals 8 pi g or 3 epsilon. This is one of the Friedmann equation, and the another one you can just use the above two equation, can easily obtain epsilon time derivative of epsilon equals minus 3 a dot over a epsilon at p, or can be minus 3h epsilon at p. It's just the two famous Friedmann equation using general relativity method. And you can see that we can just compare it with the Newtonian condition. You use the Newtonian equation here. Yes, you will find that you can if we use that the pressure equals to 0, this equation will not change, and this one is just you can just regard that parameter k to 2 times the energy, and you will obtain this will reduce the general Friedmann equation to the Newtonian condition. Yeah. And the reason is if we consider a non-relativistic limit, the pressure is much less than the energy density, and you will reduce this the Friedmann equation in general relativity's case to Newtonian ones. Okay. This is the derivative of the Friedmann equation. Let me see. Whether we have time to talk about Boltzmann equation. My equation. Maybe next time, or well, we will leave the Boltzmann equation and its conclusion next time. I think today is enough.